Now if we focus on a short math here, so let's say some values is given again and you are asked to calculate the phi m, that means the mutual flux. So we already know the formula, EP equal to 4.44 NP phi FM. So EP is already given, 200 volt, frequency is given, NP is given. So if we put all those values, then we will definitely get the shared flux or mutual flux. And similarly, now second question, find the secondary turns n suffix s. So we know the formula, EP over ES equal to, so if I zoom in, so we know the formula, EP over ES equal to NP over NS. So we know the EP, we know NP. Let me show you. Okay, so here we know EP, it is given here 200 volt. We know NP, it is 15. We know ES, which is 2400 volt. So we can definitely get the value of n suffix s from this formula. And if you notice another thing, here it is 200 volt is supplied, where we are getting 2400 volt. So a huge stepping down has been done here. So definitely you can say corresponding transformer ratio. Moving on, so now previously our expression, if I write it again here, so previously VG over VL it was A, and whereas for current it was IS over IP equal to A. So if we change it to IP over IS, then it should be 1 over A. And now if we divide this equation by this, so we can write this VG over VL divided by IP over IS equal to A over 1 by A. Now we can go further. So here if I write it, so it was VG over VL multiplied by, you can say, IS over IP from mathematical rule, and then in our right hand side it is A multiplied by A. So in our left hand side we can also change as well. So if we change it to VG over that IP, if we take here, and then again IS over VL equal to A square, then again if we get the second multiplication term to the denominator, so we can write it here IS over VL. So we just take this second term to denominator again. Why? Because we will be writing in terms of impedance. So this is basically, we can say, the primary impedance, because VG is the primary supplied voltage, IP is the current. So definitely this is the primary impedance, we can say ZP. And similarly, sorry, this should be a little mistake happened here. Anyway, so if I write it again, so this IS over VL, so whenever we will take this term to our denominator, this should be VL over IS, right? So this is basically the impedance of secondary Z suffix L. So now we can say that ZP divided by ZS or ZL, we can say also S or L, secondary impedance or the load impedance more specifically. So we are calling it load impedance since we applied it as a load voltage VL. So it was VL load voltage, so we can say load impedance, so equal to A square. So from where we can write ZP equal to A square into ZL. So here a impedance transformation is also being possible, which we call the reflection impedance or reflected impedance. So if I clear this all and move on, so this is called a reflection. And if you apply an impedance at secondary, and you can make that impedance larger or smaller at primary depending on the values of A. So you can understand that if the A is greater than 1, for example 10, so if A is 10, then definitely A square is 100, so 100 multiplied by ZL. So for that particular case, we can say that the secondary impedance, which was the load impedance, is increased to 100 times at primary. And if it is less than 1, the transformer ratio, then definitely this primary impedance, the secondary impedance will be reduced to primary. So this is what it is written here. So an impedance can be made to appear larger or smaller at the primary by placing it in the secondary of a step down or step up transformer. So if it is a step down transformer, for example, if it is A greater than 1, then definitely we notice that it will be larger, and if A less than 1, then definitely the impedance will be smaller. So this is the impedance transformation, or we can say reflection happens. And if we place capacitive or inductive load at the secondary, or at the secondary place, that is the load side, then definitely the reflected impedance is also capacitive or inductive. So moving on, our last math here. So again, some values is given and you just need to use the simple formula. So first of all, find the magnitude of the current in primary and the impressed voltage across the secondary. So first of all, it is asking magnitude of current in primary, that is IP. So if we notice here what is given, so NP is given, NS is given, and IS is also given. So we definitely use the formula IP over IS. It will be NS over NP. If you remember, I is different for others. So from where we already know NS, NP, IS, from where we can get IP. So it is calculated here, which will be 12.5 milliampere. And second question, the impressed voltage across the primary. So we need to calculate our impressed voltage across primary, that is the VG. That means what amount of voltage is supplied here, that is asked. So we can use the similar formula, that is VG over our secondary voltage VL, load voltage, equal to NP over NS. But an important point here, we can't know, right now we don't know the VL exactly, but we can calculate it, because we know that VL basically the voltage across this resistance. So we can write VL equal to IS multiplied by R from Ohm's law. So IS is given 100 milliampere, R is 2 kilo ohm. So from where we can calculate the VL value, and then if we put that value, so we will get the impressed voltage across primary. So it is 1600 volt at primary, and at secondary we are getting 200 volt. So you can say this is a step down transformer. So we are supplying a huge voltage in primary, wherever we are getting a lower amount of voltage in secondary. Last question, find the input resistance of the transformer. So here we will use the reflected impedance formula. So we already know the secondary impedance, and see, if we calculate the transformer ratio A, so A is basically NP over NS, we know. So NP over NS we can calculate, it is just 8. So from where we can use the reflected impedance formula ZP, which will be A square into ZL. Previously I just derived. So from where we can use the expression, and it will return you 128 kilo ohm. So if you notice, our load is 2 kilo ohm, but in primary side it is reflected to 128 kilo ohm. So that's all I can say. This is the reference, and for that particular reference, for particular slide, I followed most of the Robert L. Boylested book. So if you want to study further, and you should study further other than this slide, so you may refer to chapter 24 of 13th edition. So there we will get all this information, and also for some portion I also got some information from the book by B.L. Theresa and A.K. Theresa. So you can read the first reference. I think you already know it, you already have it, and if you need the second one, you can contact with me as well. So far we just derived some expressions, and we just know about transformer. And don't worry, if it is new to you, probably you will definitely get some information, some detailed information, in-depth analysis in energy conversion on course. So if you already took that course, so I think you already know these stuffs. And transformer is used in I can say in almost every scenarios in electrical and electronic engineering. For example, in power distribution, so we know that power is generated from station, for example Kaptai hydroelectric plant. So power is generated at that particular station, whereas power is being supplied to our home. Let's say my home is in Khulna, so definitely power need to transfer from that particular generating station to our load side. So in between these places there are multiple transformers. So whenever we want to send this power, so we generally increase our voltage level. So that's why we need step up transformer in generating sides, and then we transmit the power, and at the receiving end we receive it by reducing the voltage level. So in our house we know we generally use 220 volt, wherever we are generating for example 11 kV. So that is a very important example. So transformer is mostly used wherever we need voltage level increase or decrease. So thank you everyone. I can end it here. This is probably the last lecture for this course. So see you soon in any other courses. Bye bye.